Hello friends, I am Snehal and our today's topic is method of separation of variables for the solution of first order differential equations. So let us start. Now the first order differential equation can be written as dy by dx equals to some function of x and y. Notice the presence of first order derivative of y with respect to x. So because of this one, this is first order differential equation. Now in order to solve this by variable separable method, we have to try and write this f of x and y as product or division of two separate functions of x and y respectively. So let me show you how. So we will write f of xy equals to some function of x multiplied by some function of y. So g is function of x and h is function of y. Or f of xy equals to g of x divided by h of y, or f of xy equals to h of x divided by g of y. So once we are able to write this f of xy in either this form or this form or this form, then we will be able to separate the functions of x and y, and then we'll be able to integrate them separately. So some examples will make this method clear. So let us see some examples. Okay, so let us see example number 1. And example number 1 is dy by dx equals to 1 plus y square divided by 1 plus x square. Now this is simple example. Here this right hand side, which is f of xy, it is already in this form. In numerator we have some function of y, and in denominator we have some function of x. So we have some g of y divided by h of x. So all we have to do is take this function of y on the side of dy and take dx on the side of function of x. So let's do that. So we can write this as dy divided by 1 plus y square equals to dx over 1 plus x square. And now let's just integrate this. So the integral of 1 over 1 plus x square dx is, as you might know, tan inverse x. And similarly, we'll have tan inverse of y on this side. And there will be a constant of integration c. So this is the solution. Very simple. So this one is called as the general solution. So this is general solution of differential equation, and if some initial condition is given, we can determine a particular value of this constant c, and then this will be called as a particular solution. Okay, so this is how we use the method of separation variable. Let us see another example. Now let's have tan x into dy by dx minus sec square x equals to 0. Let's try to solve this. Okay, let me put this y here. Okay, so it is y times tan x into dy by dx minus sec square x equals to 0. Okay, so first thing we'll do is we'll take the sec square x on the other side. So this is y into tan x dy by dx equals to sec square x. Now let's take this tan x on the other side and dx also on other side. So the functions of y and x will be separated. So we have y dy on this side equals to sec square x, and this tan x, it is in multiplication on left hand side, so it will go in division on right hand side. So tan x, and this dx we have in multiplication. Now let's integrate this. So let's put this integral sign. The integral on this left hand side is very simple. It is just integral of y dy. So we'll have y square divided by 2. And on right hand side also it's simple. We have this tan x in denominator and its derivative is sitting in the numerator. So sec square x is derivative of tan x. So we can write u equals to tan x. Let's make this substitution. So we'll have du by dx equals to sec square x, and which implies du equals to sec square x dx. So let's substitute u in place of this tan x, and in place of sec square x dx we have du. Okay, let's do that. So we have y dy equals to du over u, and now the integral is simple on both sides. So on LHS we have y square divided by 2 equals to, on RHS we have log of u, and let's have some constant c. So because log is involved here, we'll write this constant c as log of some other thing. So let's write this as log of k, and it is natural logarithm. So we have ln. So it is ln of k. Okay, so then we have y square over 2 equals to, now we know that log of a plus log of b is log of a times b. So we have ln of k times u, and we know that u is equal to tan x. So it is ln of k tan x. Okay, and let's take 2 on other side, and then y square equals to 2 times ln of k tan x, and therefore y will be plus minus of the square root of this thing. So this is the solution. Now this is again the general solution, and if we determine the value of k, it will be a particular solution. Now let us see some problems where we determine particular solutions. Okay, now let's have as problem number 3, dy by dx equals to minus x or y. Remember, we had found this equation in last lecture from equation of circle. Okay, so we have dy by dx equals to minus x over y, and y equals to plus minus 4 when x equal to 3. Find general and particular solution for this differential equation. So this is the problem. It's very simple. So we have dy by dx equals to minus x or y. So it is function of x divided by function of y. Now let's take this y on this side. So we have y dy equals to minus of x dx, and now let's just integrate this. So integrating, we have y square over 2 equals to minus of x square over 2 and plus some constant. Let's take this x square over 2 on left hand side. So we have x square over 2 plus y square over 2 equals to this constant. So x square plus y square equals to 2 times this constant, and then we have to substitute one of these values for y when x is equal to 3. Okay, and why do we have two values? It's because this is equation of a circle. We have x square plus y square. We can write this 2c as some r square. So let me write x square plus y square equals to r square, and then suppose this is that circle. So for this x equal to anything, let's call it x equal to 3, we have this value of y as well as this value of y. This is y equals to 4, this is y equals to minus 4. Okay, now let us just substitute one of the values. So let's put x equal to 3 and y equals to 4 here. So substituting x equals to 3, we have 3 square plus 4 square equals to r square, and this is 9 plus 16 equals to r square. So we have r square equals to 25. Okay, so this one or this one is general solution, and once we substitute this value of r 2c, we have x square plus y square equals to 25. So this is particular solution, and it represents a circle whose center is at the origin and it has a radius of 5 units. So as you can see, r square is 25, so r will be 5. Okay, now let us see some examples from engineering and physics. Now let us see problem number 4, and it is based on the law of radioactive decay. And the law says that rate of decay of a radioactive material is directly proportional to number of atoms remaining at that time. Okay, and if n equals to n naught at t equals to 0, so number of atoms at the starting is n equals to n naught, then find the number of atoms n at some other time. So other time is t. Now let's try to solve this. So let us write this law in form of an equation. So rate of decay, that is number of atoms changing per unit time. So change in number of atoms with respect to time, and because it's decay, it's negative change. So we have minus of dN by dt, and it is proportional to the number of atoms remaining at that time. So this is proportional to the number of atoms. Okay, now let's remove this proportionality sign and put equality sign. For that we need a constant, so lambda is a constant here. So we have dN by dt equals to lambda n. Let me take that minus sign on other side. Now this lambda is called as decay constant. So lambda is the decay constant, and it is characteristic of a particular radioactive material, so it is going to be different for different materials. Okay, now we have this equation, the differential equation dN by dt equals to minus lambda times n. Now let's take this n on left hand side, and let's have function of t on right hand side. So we have lambda, which is constant, times dt, and let's integrate this. So on LHS we have 1 over n dn, and integral of that will be natural log of n. So it will be equal to, lambda is a constant, let's take it out, integral of dt is t, and plus we'll have some constant. Now because the logarithm is involved, let us write this as ln of c. Okay, so this is ln of c. So this is the general solution. Or we can take this ln of c on the other side. So we'll have ln of n minus ln of c equals to minus lambda times t. Then ln of n minus ln of c is ln of n divided by c. So this is equal to minus lambda t. Now we can remove this log. So on right hand side we will have exponential. So n over c equals to e raised to minus lambda t, and let's take c on other side. So we have n equals to c times e raised to minus lambda t. So this is other form of the same general solution. Okay, and how can we determine c? So by using this condition given in the problem, so we could have some other number like 2, 10, 15, 100, 1000 in place of n naught. So it could be a particular solution for that number, but now we have some n naught here. So at t equals to 0, we have n equals to n naught. Substituting that, we have n equals to n naught equals to c into e raised to minus lambda times t, which is 0, and anything raised to 0 is 1, so this term is 1. So from this we get c equals to n naught, and let's substitute that here. So we have n equals to n naught e raised to minus lambda t. So this is the particular solution, and it gives us number of atoms at any given time. Okay, so now let's see another example. Okay, so let's see this last problem for today, and it says we have RC circuit, that is L equals to 0. So we have inductance equals to 0 with V equals to 0. So we are not giving any potential difference to the circuit. Find Q as a function of t if Q naught is the charge on capacitor at t equals to 0. So let's draw that circuit. So we have RC circuit, so we have resistor, we have capacitor, but we don't have inductor. So this is R, this is C, and this is the applied voltage, which is V equals to 0, and it cannot be sinusoidal. So let's have this V equals to 0 as the applied voltage. Okay, now I can write the applied voltage V equals to the voltage drop across capacitor and voltage drop across the resistor. So it is Vc plus Vr. So we have V equals to 0 equals to Vc is voltage across capacitor, and voltage across capacitor is given by Q divided by C, plus Vr is voltage across resistor, and voltage across resistor is given by Ohm's law. It is I into R. And we are writing these lowercase letters which tell us that these quantities depend on time. If we write Q and I, so these values are written for constants, and we take lowercase letters for the variables. Anyways, now I can take this IR on left hand side. So we have IR equals to, or minus IR equals to Q by C. So IR equals to minus Q over C. Let's take R on other side. So I have I equals to minus of Q over RC. And we know that current is equal to change in charge over time. So this is dQ over dt equals to minus 1 over RC multiplied by Q. Okay. Now let's imply the separation of variables. So let's take Q on this side, dt on the other side. It's similar to the last problem. So we have dQ over Q equals to minus 1 over RC times dt, and let's integrate. So this RC is a constant. I have kept it outside the integral. Integral of 1 over Q dQ is just ln of Q equals to minus 1 over RC, which is there, times integral of dt is t, and plus there will be some constant of integral. Okay, so log is involved. Let's put this constant as ln of some other constant, or ln of c. Okay, now we can take the c on the other side. So we have ln of q minus ln of c equals to minus 1 over RC times t, and ln of q minus ln of c is ln of q over c, and that is equal to minus 1 over RC times t. Okay. Now, if we have to remove this logarithm, there will be exponential on right hand side. So we can write this as q over c equals to exponential of minus 1 over RC times t. And let's take c on other side. So we have q equals to c e raised to minus 1 over RC times t. So this is again the general solution. Okay. Now let's substitute the initial condition. So initial charge on the capacitor is Q naught. So when t equals to 0, Q equals to Q naught. Let's substitute that. So we have Q equals to Q naught equals to C e raised to something into 0. So it is e raised to 0, which is 1. So which implies C equals to Q naught. And let's substitute this in this equation. So we have q equals to q naught e raised to minus 1 or rc times t. Okay, so this is the particular solution. So this is the method of separation of variables for the solution of first order differential equations. Now every time we cannot use this method simply because every function of x and y cannot be written as product or division of two separate functions of x and y. So the next time we will see how to solve homogeneous differential equations where we cannot use this method. So till then, please try few problems on the separation of variable method. Thanks for watching the lecture.